We treat electricity like a domesticated utility, but underneath the copper and plastic, it is a highly volatile force that constantly seeks a way to break its containment and destroy its surroundings. Containing that force took decades of engineering. We had to evolve our physical defenses through 3 distinct stages, starting with thermal melting, advancing to electromagnetic sensing, and finally mastering residual balancing. This animation shows the baseline state of a healthy electrical circuit. Everything is in equilibrium. Electrons flow evenly from a power source, do their work at a load, like lighting a bulb, and return safely along a designated path. As long as that loop stays intact, the energy is safe. The entire history of electrical engineering is essentially an arms race to build sensors that can detect the exact millisecond this baseline loop fails, before the escaping energy causes a catastrophe. The first major threat engineers had to solve was the overload. If you plug too many high-draw appliances into a single circuit, you pull an immense amount of current through the wires. This generates rapid heat, degrading the plastic insulation and quickly igniting the surrounding materials. The earliest technological defense to stop this was the fuse. It is a deliberate, engineered weak point placed directly in the path of the circuit. Fuses rely on a simple physical reaction, the heating consequence of current. As the system overloads and temperatures rise, this specific wire is designed to soften, melt, and physically snap. This severs the connection entirely, killing the power before a house fire can start. While effective, the fuse is primitive. It protects the system by completely destroying itself. Having to manually replace a burnt piece of metal every time the grid fluctuates made it far too slow and sacrificial for modern, high-demand power grids. Engineers also had to deal with a much more violent threat, the short circuit. This is a fault where electricity bypasses the load entirely. Without that resistance, the voltage approaches infinity and the current spikes explosively. The solution was the miniature circuit breaker, or MCB. Instead of melting, this is a reusable mechanical device engineered to handle both the slow heat of an overload and the explosive surge of a short circuit. This MCB cross-section shows 2 mechanisms. For overloads, a bimetallic strip above the plates bends under heat to unlatch the connection. Short circuits happen too fast. Instead, focus on the central red.
For part 2 of this video, comment part 2 in comments. Thank you for watching. Keep growing every day with just a bit of knowledge. Like and subscribe for more content and continuous learning.